So on question 55 and 56, both of these things go together. You see yourself a right triangle here, and you have probably been trained up to this point. If I see right triangles, I'm thinking the Pythagorean theorem. And you'd be absolutely correct in that line of thinking. We're going to use the Pythagorean theorem in order to solve these two right triangles. So Pythagorean theorem is called the Pythagorean theorem, N-R-E-N, theorem, after a Greek mathematician named Pythagoras. And lived, ages and ages ago. In geometry this year, we will formally understand what the heck this whole theorem thing is about. This is probably the first time you'd ever heard the word theorem attached to anything in mathematics, but they're super important. And we'll also look at why the Pythagorean theorem actually works as intended. But at this point, you just learned how to use the thing. Okay, anytime we have ourselves a right triangle, which can be easily identified by the official red box that everybody puts right there in the corner, and then we traditionally label the legs are the two sides of the right angle here, with an A and a B. And the hypotenuse is always across from the right angle. It's also always the longest side of that right triangle. And the reason for that is because the biggest side of a triangle is always across from the biggest angle, and the 90-degree angle is the biggest angle in a right triangle. Again, I'm going to kind of label this thing as hypotenuse. Greek word, that's why it sounds weird. And it goes a little something like this, that a squared plus b squared is equal to c squared. All right, and like I said, we will see why that's true this year in honors geometry. In the meantime, when you're using the Pythagorean theorem to solve a right triangle here, most importantly, you want to make sure that c goes in for c squared, all by itself, and the two legs go in for your a and a b. Of course, they're not going to be labeled with a, b, and c. You just have to make a judgment which one is going to go where. So the most important thing is to identify where the hypotenuse is so that you can put that thing in for c. Now, when you're using the Pythagorean theorem, you're either going to work it forwards or you're going to work it backwards. Working it forwards usually means that you're given the two legs, you'd put them in for the A and the B, and you'd be solving for C. So as an example, let's say that I had something like this, A3 of 4. You probably already know what C is, but let's pretend for a second that you don't. All right, if I were to take this 3 and call it A, and the B for 4, and those two don't matter, they're interchangeable. But what is not interchangeable is the hypotenuse. It has to be the number that's all by itself. Okay, so now where I put these numbers in here, I would have a 3 squared plus a 4 squared, and that should be equal to c squared. Order of operations is going to dictate that I'm going to square these things and add them together first. So 3 squared, I get a 9. 4 squared, I get a 16. Now I have to add them. 9 and 16 gets 25. That's 225. Come on. And then finally, I have to do the inverse of squaring, which is taking the square root of both sides, so I can get my c here and here. And then I would have c is equal to 5. C equals 5. Now, like I said, you may have already known that this was 3, 4, 5. This is something that we call a Pythagorean triple. Pythagorean triples are three whole numbers that work in the Pythagorean formula, a squared plus b squared equals c squared. And this is an uncommon kind of thing. Now, even though I say it's uncommon, there's an infinite number of these Pythagorean triples. But it's uncommon because not just any number works. So for example, would 1 and 2 and 3 work in the Pythagorean formula here? Here, let's just give it a try. If I try to put 1 squared plus 2 squared, is that equal to 3 squared? 1 squared is equal to 1, 2 squared is equal to 4. but 3 squared is equal to 9, and that absolutely does not work, right? So it's a very interesting, cool thing that happens whenever you have whole numbers that make up the sides of a right triangle. We call those things Pythagorean triples. Okay, this is an example of working the Pythagorean theorem in a traditional sense, given the two legs, and then working backwards, not working backwards, working forwards here in order to find the length of the hypotenuse. Okay, and that's essentially what's happening here on number 55. We have the two legs, and we need to find the length of the hypotenuse. But over here on number 56, it's kind of backwards. We already have the hypotenuse, and we're looking for one of the missing legs. So let's do an example of that kind, if my pen would work. There it goes. Okay, and I will just at random pick some. Wait, did I put some? Just now notice this. This was not an official red box. Okay, now we're good. Pretend it never happened. This time I'm going to make my hypotenuse equal to, let's see, how about something along the lines of 10? And then let's say that one of my sides here is equal to 8. And then we want to find out what this other missing side is, which I'll just go ahead and call an A. It could have been a B, could have been an X, it doesn't really matter, it's a variable. I want to make sure that I understand that 10 up here is the hypotenuse, it's the C, it's going to go in the Pythagorean formula all by itself, and then we'll make the 8 equal to a B. So putting these things down into the formula, we've got an A squared plus an 8 squared is equal to 10 squared. How this is different, of course, is that up here on the first one, you would square and you would add these two squares together, which is where we got our 25. After we square these two things together, we're not going to add them together. We have A squared plus 8 squared is 64, 10 squared is 100. And now to isolate the A squared term, I have to get rid of the 64, which means I'm going to have to subtract it. So instead of adding the two squares, I'm going to end up subtracting my two squares. A squared is equal to, let's see, 100 minus 64. Let's see, that'd be a 40, but it's less, so 36 is 36. Hey, look, we're going to get another neat whole number. This is A, after I take the square root, is equal to 6. And you can see that we found ourselves another Pythagorean triple, a 6, 8, 10. But really, 6, 8, 10 is the same thing as the 3, 4, 5. It's just been dilated or scaled up by a scale factor of 2. If you take all of these sides, 3 times 2, 4 times 2, and 5 times 2, you get this one that I just made right here. Anyway, this is, that's kind of, again, it's kind of an uncommon thing. You're not going to always expect to get whole numbers whenever you're using the Pythagorean theorem. You might get some sort of irreducible square root, or maybe a square root that you have to simplify or approximate in the calculator in some way. Anyway, that's the kind of thing that you're doing on number 56. You already have the hypotenuse, so you'll have to kind of work backwards here, subtracting the squares instead of adding the squares like you have to do on number 55.